Today we want to talk about differentiable. Now you guys have already heard about limits, you've heard about continuity. The next step of this puzzle is whether or not a function is differentiable. Now if you think about the word differentiable, it ends in ABLE, which means we are able to do something. In this case, we are able to be different. In mathematics, when you're able to be different, all that means is you're able to change. And if you can change, then you have a derivative. So the word differentiable is all about finding out whether or not your function has a defined derivative at a certain value. So we want to look at a couple of examples today and figure out what prevents a function from being differentiable. In other words, what prevents a function from having a slope? If you think about a typical f of x, what we're talking about is a curve like this, and if we ask, does f of x have a slope? Is f of x differentiable, in other words? All we're asking is, as we walk along this curve, can we draw a tangent line that has a defined slope? So most functions follow the rule that they can have a slope, they can be differentiable. So instead of thinking about what makes a function differentiable, let's turn it around. Let's talk about what prevents a function from being differentiable. So when you think about slope, what's the one slope we're not allowed to have? Well, if you think about a line going like this, we're horizontal. We've got a slope of 0. Anything that goes like this, we know that there's a defined slope. The problem we get into is when we go vertical. A vertical slope is undefined. That means if you have a tangent line that's vertical, you will not be differentiable. So one of the big problems to differentiability is vertical tangent lines. Okay, so that is one thing that can prevent your function from being differentiable. Now, this function looks like a polynomial, nice and smooth. It's going to have well-defined slopes everywhere we look. Let's take a look at another example. What happens if in our next function we have something that's not quite as smooth? What happens if in our next function we have something that comes to something like this? Okay, now this is still a function. It's well-defined everywhere. Okay, it passes the vertical line test at every single point, and it's continuous. Now let's talk about continuity for a second, because differentiability is built on top of continuity. So if we're talking about continuous, think about what is our definition of being continuous. Well, a function is continuous if the limit as x approaches a from the left of that function, and the limit as x approaches a from the right of that function are equal. Okay, now that's a start. You may remember that from being the definition of limit, but to be continuous, you have to go one step further, because all this really says is, as I come from the left and I come from the right, I'm going to kind of end up at the same value, but we don't know whether or not that's filled in yet. So to finish the definition of continuity, we've got to have this equal to f of a. In other words, when we go to find the y value, we're going to find it in the exact same place the limit predicts. So that's our definition of continuity. This is a bedrock principle that differentiability is actually built on, because, first of all, you've got to be continuous to have a slope. If you're not continuous, if you don't have a point, you can't have a tangent line at that point. If you don't meet from the left and the right, you can't have a slope at that point. So to be differentiable, you must be continuous. That's always the first piece of being differentiable. When you look at this guy, we satisfy the continuity. This thing is continuous everywhere. But if I were to ask you, is there a place here that looks kind of out of the ordinary, looks kind of strange to you, that kind of sets off your alarms? Most of you are going to say, yeah, what's going on right here? This is not smooth. Okay, that's what we like to say. We like to have a smooth curve. There's a really, really jagged change here. This is what we've got to be concerned about. This is something that's going to prevent differentiability. Now let's think about why. Let's think about why. If we were to look at just this part, everywhere along here, you're going to have a nice smooth tangent line. Okay, you're going to be able to draw. You're not going to have any problems whatsoever. And if you come from this way, everywhere along here, you're going to have a nice smooth tangent line. So tangent lines are good all over this place, and tangent lines are good all throughout this interval. The one question we have is what's going to happen to the tangent line up here? Well, if you think about this, and this is how I like to do it, I think of my tangent lines as being a direction. And a direction is the way I'm looking as I'm traveling along that line, that curve. So we're going to take BBA and put it over here. We're going to take his boss, Mickey Mouse, and put him over here. And the question we're going to ask is, where are they looking? Where are they looking? Now, let's just start back on this curve, the kind of curve we started the example with this guy. If I want to know if I was differentiable right here, if I put Mickey here and BB-8 here, well, right now Mickey's looking in this direction, BB-8's looking in that direction. But what's going to happen as they get closer and closer to this point right here? Well, as BB-8 rolls along, by the time it gets to here, he is looking in that direction. When Mickey gets to that value, he's looking right back at BB-8. What that means is they are looking in the same direction. That is the equivalent of saying that tangent lines are going to have the same slope as we approach this point right here. This is the key to differentiability, making sure that your tangent line slopes agree as they come from the left and as they come from the right. If we go back up to this example now, and we do the same idea, when Mickey gets to that point right there, he's kind of looking in that direction, and when BB-8 gets there, he's kind of looking in this direction, which means the tangent lines will not agree. The slopes of the tangent line will not agree. Whenever the slopes of the tangent lines don't agree coming from the left and the right, that function is not considered to be differentiable. So now we've got the idea, you got kind of the thought process behind it. Let's take what we've done, let's put it in the language of love, let's make sure we can write it using good mathematics. So, to be differentiable, what are we saying? Well, it's basically this. Mickey has to be looking at BB-8. The left side slope has to be the same as the right side slope. So, it sounds a lot like continuity. We've got this idea of coming from the left, we've got this idea of coming from the right. But in continuity, it wasn't the directions that had to be the same. It was the y values that had to agree. So that's, again, this point is part of a continuous function. Mickey and BB-8 will end up at the same point. They're just going to smash into each other because they're not going to see each other, they're not looking at each other. That means we've got continuity. First step of being differentiable is having continuity. We are continuous here. But the second step of differentiability is making sure that BB-8 and Mickey Mouse are looking directly at each other. And that is the part this fails. So how do we write that using good mathematics? Well, let's take a look. Mickey was coming from the left side, okay? Anytime in calculus you're talking about coming from the left side, that implies doing a limit. So we've got to take the limit as we approach that value, which I'm just going to call A for now, it's going to be any value, from the left. Okay, so there's my good notation. Now, what is it we're keeping track of? It's not the y values, it's the slope. What's the way we say slope when we're talking about calculus? Well, if you've got a function, the slope is the derivative of that function. So we want to keep track of what is f prime of x doing as we come from the left. Okay, that's Mickey. That's going to tell me the direction he's looking in. Now we got to do the exact same thing for BB-8, but this time, we're not coming from the left, we're coming from the right. So just a little plus sign up there on the 8, and coming from the right. Now, again, it is the slope that we are concerned about. If these guys are equal, our function will be differentiable. So this is really the key idea behind differentiability, that when you come from the left and you come from the right, you're going to be looking at each other at that point. Keep in mind, you must have continuity to get differentiability. If you fail continuity, you don't even have to do this. You know you're not differentiable right away. So let's take these ideas, let's put them into practice. Let's look at a couple of examples. The next example, the first example we're going to look at. Okay, kind of a straightforward one. And that's going to be f of x is equal to x to the 2/3. Now, this is going to be more of an analytical kind of problem. We're going to work it out using our math symbols. If I want to find out if a function is differentiable and they give me an explicit function, I just take the derivative. I'm going to take the derivative, I'm going to look and see what happens with the derivative. So, in this case, our prime of x is going to equal, using our x to the n rule, that's going to be 2/3 x to the 2/3 minus 1. which will turn out to be 2 over 3x to the 1/3. So now, let's take that one step further, make 3 times the cube root of x. If I were to ask you, is this function going to be well defined everywhere? Hopefully you would realize that this particular function, which is the derivative in this case, is going to have a domain problem. X cannot equal 0. There is no way x can equal 0. If x equals 0, that means our slope is undefined, and that means we're going to have a 0 in the denominator for the slope. So the slope would end up being something along the lines of 2 over, well, 3 times the cube root of 0, but that's really 2 over 0. We know that is our undefined slope. We got a vertical tangent line here. That's what's going on. Now, you can take a few moments and you graph this. The graph of x to the 2/3 comes in this way, looking great. Right now, all of this is differentiable. And you can see any negative input is still going to work, because when you do the cube root of a negative, you can get an output. So we are going to have slopes everywhere along this. And what happens is it comes into the origin. It gets really, really, really very steep there. And now, on the other side, we're going to get the mirror image. And you can see that this is nice and smooth on the left side when x is less than 0. Same thing when x is greater than 0. But when x equals 0, we're going to have Mickey looking straight down. We're going to have BB8 looking straight down. They may agree. You might argue that they're going to be looking the same way, but it's going to be looking straight down. If you're looking straight down, you're vertical. And if you've got a vertical tangent line, you are not differentiable. So if you're given an explicit function, take the derivative, and basically what you're going to do is you're going to look at the domain of that derivative. Wherever that derivative exists, the function is. So this is how you do it analytically. But to be honest with you, the way the calculus exam likes to present this is slightly different. They like to present it kind of using the idea of the left and the right. And the only way that becomes interesting is if you're working with either a graph or a piecewise function. So let's take a look at this next example. So in this next one, we're going to be looking at a piecewise function. And the reason the piecewise function goes hand in hand with differentiability and continuity is because the piecewise function is the only time it's interesting when you're coming from the left and coming from the right. Because when you've got a piecewise, the rule on the left-hand side can be different than the rule on the right-hand side. And that means we've got to check to see if they match up. Let's take a look. What happens if we're given the function f of x equals, and we're going to do x squared minus 2x plus 1 when x is less than 2, and then we're going to do x cubed minus 10x plus 13 when x is greater than 2. So let's put the equal sign on the first one. In this example, you've got a degree 2 everywhere when x is less than 2. You've got a degree 3 everywhere when x is greater than 2. They're both polynomials. We love polynomials as examples. Polynomials are always continuous. Polynomials are always differentiable. So everywhere before 2, we know this guy is going to be fine. Everywhere after 2, we know this guy is going to be fine. The only question we have is what's happening at 2. So the way we're going to approach this is the steps to finding out if a function is differentiable. Number 1, check the continuity. Number 2, check the slopes from the left and the right. So in this example, as we check the continuity, all we've got to do is say, let's look at the limit as x approaches 2 from the left. Now, when we're doing x approaches 2 from the left, we're using this rule right here. This says, hey, use me anytime x is less than 2, and that means from the left. So we're doing x squared minus 2x plus 1. We're not going to take that exact same limit, but this time we're going to take it from the right. And from the right, we're going to be using this bottom expression because this says use me anytime x is greater than 2, in other words, when x is to the right of 2. So we're going to find the limit of x cubed minus 10x plus 13. The last part of continuity is making sure the function exists at the value, so we're actually going to do f of 2. But in this case, f of 2 says use the top rule, so we are going to plug in something squared minus 2 times something plus 1, and we're going to plug in that 2 value. If all three of these things agree, we know we're continuous. So in the first round, we're going to get 4 minus 4, which is 0 plus 1. In the second round, we're going to get 8 minus 20. 8 minus 20 is negative 12. Negative 12 plus 13 is 1. So we know that they're going to meet from the left to the right. It's either going to be a hole there or it's going to be filled in. This is going to determine whether or not we've got a hole or filled in. This tells us as we plug in 2, the actual y value we get is 1 as well. We know we are continuous, okay? So now the function, it meets, it's connected. The next question, do the slopes agree when we're coming from the left and coming from the right? So when we look at this example, what we've got to do is we've got to take the derivatives. So here we go. We want to ask the limit as x approaches 2 from the left. And that was the equivalent of asking, what's Mickey doing? He was coming from the left. Well, we want to know where he's looking. We want to see the direction. That means we need the derivative of this function. So the derivative is 2x minus 2. So that's what we're using here, 2x minus 2. Now, BB8's up next. He's coming from the right side, so he's approaching 2 from the right. Which way is he looking? In other words, what is his slope as he's approaching? This function is going to tell us the slope by taking its derivative, so we're going to get 3x squared minus 10. Now we've got our 2 slopes. This tells me the slope everywhere to the left of 2. This tells me the slope everywhere to the right of 2. We want to know what's going on at 2. Well, as these guys meet, the limit as we approach 2, in this case, is going to equal 2. And the limit as we do this one, let's see, 2 squared times 3 is 12 minus 10 is 2. We have now shown the limit of the derivative from the left of 2 is equal to the limit of the derivative from the right of 2. That is differentiability. These two things together tell me that this function is differentiable at x equals 2. And then looking at the individual pieces, because we were polynomial, because polynomials are always differentiable, we actually were differentiable everywhere from negative infinity until 2. And this is we're differentiable everywhere from 2 to infinity. This tells me we're differentiable at 2. That means this function is differentiable on the entire real number line from negative infinity. We're going to look at this one more way. We're going to look at this graphically, okay? But before I leave this is the key to differentiable. You do continuity first, you do differentiability second, and you make sure your limits agree. The AP exam loves working with differentiable in this fashion, giving you a piecewise function and making you show them they agree. One of their favorite questions is to throw a little unknown in here and then ask you what's the value of the unknown that makes them continuous, that makes them differentiable. And that means you're going to end up with a couple of equations and you're going to have to solve them simultaneously. Very popular question. We're going to look at this graphically before we wrap up. So let's back up. And let's put another graph of a function up here. And if we think about this graphically, this is what differentiability is all about. I call it smooth. That's a very common name for the curve that looks like this. Any curve that is smooth, what it means is for every point when we come from the left and the right, we're going to agree not only with a y value, so it's continuous, but we're going to agree with the direction we're going in, so it's differentiable. So this is kind of like a nice version of a function that's always going to be differentiable. Where does it get messy? It gets messy when we do a curve that changes really abruptly. Okay, something like that. Or what if it continues on this way, goes down, and then spikes up that way. Okay, this function has some differentiability issues. He will not be differentiable at this value of x or this value of x. These shapes, these abrupt changes in slope, we have a name for them. They're often either called a cusp or a corner And anytime you see a cusp or a corner, all it means is when you take the limit, as x approaches that value from the left of the slope of the derivative, it will not equal the limit as we approach that value from the right of the derivative. In other words, they are differentiability busters. Anytime you see these abrupt changes, that's significant. Pay attention to those, because if you have an abrupt change like that and the AP exam asks you a question on differentiability, this is going to be where you get into trouble. These guys will prevent differentiability because they are the places where the slope from the left doesn't equal the slope from the right. So the last thing we're going to do is just recap. To be differentiable, first, you got to be continuous. After you're continuous, you got to make sure the slopes agree from the left and the right. So differentiable, here are the two things. Number one, continuous function. And that means the limit as x approaches a from the left of the function, because we're talking about the y values agreed here, equals the limit of f of x as x approaches a from the right. And then again, that just means they meet. You got to make sure the point's filled in. It's going to be filled in by having f of a agree. That is continuity. Without this, no differentiability. You got to have this first. Then the second thing you got to check is the slopes agree. And the way we're going to do the slopes is going to be very similar. Which way is Mickey looking when he comes from the left? Well, that is the slope of that function. And then which way is BD8 looking as he comes from the right? That is the slope or the derivative. Those two things must be equal. If you get both of these things and they agree, we have differentiability. I hope that makes sense to everybody. Please take a look. If you have any questions, leave them in the comments. I'll be happy to try to get back to you. Thanks so much.